topic for today's lecture is electromagnetic waves. And to do this, I'm going to go beyond the scope of the course in terms of the mathematics, because to me it's the most efficient way to derive a wave equation for electromagnetic waves. To do that, I'm going to introduce three mathematical operations for you to examine. And then I'm going to rewrite Maxwell's equations instead of integral form as you're used to, I'm going to write them in differential form. Start with, we have three vector operations, or three operations. First is the divergence of a vector. It's just, it's a scalar, and it is just the derivative of each component of the vector with respect to its particular component. So it's dx, dA sub x dx plus dA sub y dy, partial of a z with respect to z. And of course, the outcome is a scalar. The second operation you may be familiar with, or maybe not, is called the curl of a vector. The curl of a vector is we set up a determinant where we have the components I, j, and k as usual when we do a cross product. The second row is, of course, the familiar del operator, ddx, ddy, ddz. And of course, in the third row are the three components of some vector A. And of course, when I go through the cross product, the ith component becomes the derivative of the z component of A with respect to y minus the derivative of the y component of A with respect to z, I, plus same thing for j and the same thing for k. The third operation that I'd like to introduce today is the Laplacian. That's what happens if I take a scalar and I have I take two derivatives of that function with respect to x, with respect to y, and with respect to z. Another way of writing Laplacian is equal to del dot del phi in this case, would be another way of writing the Laplacian. With those three operations, what I'm going to do is rewrite Maxwell's equations in differential form in cases where there are no charges or currents present. So we're going to do really simple form first. So if there are no charges or currents present, Gauss's law for electromagnetism becomes del dot E equals 0. Gauss's law for magnetism, as always, is del dot B is 0. Faraday's law, I can write in this way, minus dB dt, so that the cross product, or I should say the curl of E, is equal to minus the time derivative of B with respect to t. And then finally, Ampere's law, as modified by Maxwell, there's no conduction current, so the only term I have is Maxwell's addition to Ampere's law, mu naught epsilon naught times dt. Now, I'm only doing this because I would like to show a very easy way of showing how we can produce electromagnetic waves by either a changing electric field or a changing magnetic field, or actually both. So let's do that. I'm going to start with this vector identity. And here it is. We'll do it for electric fields first. Del cross E. If I take del cross E and then take, once again, this is what we call the triple vector product, del cross E, I can write this identity as del of del dot E minus Laplacian of E. If I do that on the other side of the third Maxwell equation, the Faraday's law, I would get del cross minus dB dt. Which I could also write, interchanging the two derivatives, I could write this as the time derivative of del cross B. Now I go to the fourth equation, and I see del cross B has an expression dE dt times mu naught times epsilon naught, so I'm going to write that in. So I have del cross minus dB dt is equal to mu naught epsilon naught dE dt. And therefore, I should say, second derivative of E with respect to t. And lo and behold, if I look at the left side, since this is 0, if I have no charges in space, I have the following. I have del squared E is equal to 1 over, I should say, epsilon naught, mu naught epsilon naught times the second partial of E with respect to t. Now this is pretty significant because we studied wave equations earlier in the course. And you notice this looks exactly like a wave equation. We have second order derivatives in space, second order derivatives in time. In a normal wave equation, this term right here would be 1 over the velocity squared. What this is saying is, and this is extremely suggestive, is that mu naught times epsilon naught should give me 1 over some velocity squared. Well, a little bit of work on the calculator would show you if I multiply these two numbers together, what I would get is that the velocity is exactly the speed of light, or 3 times 10 to the 8th meters per second. So this is amazing. What Maxwell concludes at this point is that light itself is an electromagnetic wave. This is a disturbance traveling through space. In this case, it's changing E fields. We could derive the exact same type of equation for changing B fields, and again, the velocity of the wave would be predicted to be 3 times 10 to the 8th meters per second. At this time in history, in the 1860s, when Maxwell published his work, the speed of light was fairly well known. So this was an amazing discovery. Maxwell unified electricity and magnetism with his modification of Ampere's law, and now what he was able to do with his theory is to predict the existence of electromagnetic waves.